So the topic for today is, how do you use Nsight Compute to analyze the performance of a kernel? This is a deep topic, and I can't cover all possible aspects of this in one session, but I'm calling this an introduction. And then if there are, if there's interest or demand for a follow-up kind of advanced kernel analysis session, we could do that. But I at least want to give people a mental, a frame for how you can do this process. And I'm just going to do this today as a live demo, so I don't have slides. I just want to step by step walk you through my thought process for how to analyze the performance of a kernel using Nsight Compute. Now, in particular, one thing that this will not be is an introduction to the larger GPU performance analysis world. So normally, when people are getting started with GPU performance analysis, what I say is you start with Nsight systems and then look at the timeline of your application, and then make sure that you figure out what is the bottleneck to your application. It could be a GPU kernel, but often it's something else like data transfers. And so in that case, you'd want to go ahead and optimize those things first. But I'm going to start for today's lecture or demonstration, assuming that you've already gotten to the point where you know that a GPU kernel is the thing that's the most important performance constraint in your application. And I want to talk about how you go about thinking about asking the question, how is the performance of this kernel? And in particular, we can think about it in terms of, how is the performance of this kernel relative to what I know the peak possible performance of the GPU is? So we know some things about GPUs. We can look at things like their total memory bandwidth, or their peak floating point compute throughput. And then from there, we can measure the actual memory bandwidth that we achieved, or the actual compute throughput that we achieved. We can compare the two things and see how we did. One thing that I want to say is that this is not the only possible way to think about performance. And in fact, arguably, it can be a misleading way to think about performance in some cases. And the reason is that comparing how you do to the peak throughput of the GPU that is known tells you how efficient your code is relative to the most efficient possible version of your code, but does not really tell you how to rewrite your algorithm to do something differently. So I'll talk a little bit about roofline analysis today, this idea of comparing the performance of your kernel relative to the peak possible throughput. But I want to emphasize that don't treat this kind of analysis as the only possible way to think about a kernel. Ultimately, whenever you're doing kernel analysis, you have to have some insight as the programmer to know your algorithm, right? You have to know something about your algorithm and be creative and be able to think about ways to completely change what it's doing to maybe get the same result, but in a different way. That could open up a whole new landscape of possibilities, but those are things you can only do when you know your kernel. And so I would generally say that there is no substitute for actually understanding what your code is doing. However, let me at least teach you today some things about what you would do in the generic, like what do I do when I'm encountering a kernel that I know nothing about, right? How would I use Nsight Compute to tell me something about what that kernel is doing? So that's what I'm going to talk about today. We have, NVIDIA has worked with NERSC in the past to present on this topic several times. And so we have picked a couple examples that we believe historically are useful for helping emphasize this point. And we've put these examples in this repository that I have here on, that's right up there on NERSC GitLab. And so the name of the repository is called Roofline on NVIDIA GPUs. And if you want to follow along, the idea with this session is I will talk for about 45, 50 minutes, depending on how long it takes. And then you will have time to try this out in the hands-on manner. So I'll just kind of sit around and answer questions as we go. But so you don't have to follow along with what I'm doing right now. If you want to just watch and then do hands-on later, that's great. I'll try to go slow enough so that if you are following along hands-on, you can do so. So of course, the first step is just to download the repository. And so I'll just throw the link up there in the Zoom chat. Now I'm going to be choosing to do these exercises on Theta GPU. And so that's, I will show examples that I will walk through it on there. the steps that you would do on Core GPU are basically the same. At the end of the day, the thing that we're going to have to do is load the NVIDIA HPC SDK. And so that will just be the main, like getting the node, getting the GPU, and loading the software will be the main difference between the two things. So I'm going to go ahead and clone this repository. One thing about this repository is that we chose, there's two things that I'm going to walk you through. One is some toy kernels that like are extremely simplistic and help elucidate some basic aspects of like what relevant performance limiters are in GPUs. And the other one is an example kernel that was chosen from the Berkeley GW quantum chemistry code. And so that code is, or that kernel that comes from that example uses a very large input data set. And so this clone can take a little while because it's downloading a 500 megabyte file or whatever. So if that takes a while, that's why. Once you're inside the repository, check out the branch called NV-Fortran. This just has a minor fix in the repository because this was written a while ago before the HPC SDK was available, and so like the make file in here still refers to the old PG Fortran name. Just go ahead and check out that branch.
Max, could you increase the size of the font or just zoom in a little bit?
I should be able to. Let me see if I can do that. Is that more readable?
Yes, thank you.
Okay. So I've checked out the NV-Fortran branch, again, just a minor difference. And then I'm on Theta GPU. So what I'm going to do is make sure that I have the NVIDIA HPC SDK in my path. And so the way that I could do this on Theta GPU is if you look in soft HPC SDK, that's where this lives. And so you would do module use soft HPC SDK, and then module load NVHPC 21.7 is how you would get this loaded on Theta GPU. If you're on Core GPU, you don't need to do any module use command, just use module load NVHPC 21.7. You can see this taking a little while, but should process momentarily. Actually, I can be a little bit more clever about this and do that. So if you're on Theta GPU, and then module load into HPC 21.7. Okay, so now I should have NV-Fortran in my path. So NV-Fortran is the NVIDIA HPC SDK Fortran compiler. And the reason I needed that is that later on, the example that I'm going to give is from Fortran, because that's the language that this code from Berkeley GW was originally written in. So it's a Fortran example, and it uses OpenACC. But most of what I'm going to talk about today has nothing to do with like what programming model you chose. Okay, so we've got our environment set up. We should have both NV-Fortran and NVCC in our path. And then we want to give a couple of examples of how to use these tools, Nsight Compute, I mean. So in this repository, there's an example codes directory. And then this example codes directory has the two cases that I'm going to work with. So this first code is just a simple CUDA C++ code. And then the second code directory, GPP, is this Berkeley GW example that I'm going to show you. So let's first go through a couple toy kernels in CUDA, just to warm ourselves up, just to think about how to use the tool and to understand what it says about kernels that we think that we can understand analytically, and then compare it to the tool output. So we can go ahead and compile the kernel abc.cu. It's so named because there are three kernels named kernel A, kernel B, and kernel C, which each have different performance characteristics. And so we will go through each one of those in turn. So you can see I'm just going to go ahead and compile the file. And then I have this kernel ABC in my path, and I can just verify that I run it and it works. So normally when you're starting, right, you would always profile with Nsight systems and you would get some information about which kernels ran. And so this should verify that in fact, there are 3 kernels in this application that, like I said, are named kernel A, kernel B, and kernel C. And I did not get my stats output. I am not sure why that is, but it's okay, because we can just go ahead and do the same thing with NCU. So one thing that Nsight Compute will do if you just run it in its default mode is it will profile every kernel and then give you some information about all 3 of them. So I'm not going to, for the most part, look at the standard out output. This is just what I'm going to start with, just so you can verify that the thing is working. If you just do NCU and the name of the application without any flags, it just prints the result out to standard out at the end. And so you'll get a kernel output for each of the 3 kernels that are in this application: kernel A, kernel B, and then kernel C. When you're looking at the output of Nsight Compute, it breaks up the output from the tool into what are called sections. Each section does a different kind of analysis that tells you something about the kernel that you're looking at. And the name of the section usually summarizes what kind of information you're about to look at. The first and most important section that you always start with is called the GPU speed of light section. The speed of light section summarizes the high-level aspects of how your kernel ran, and in particular, tells you what your kernel did relative to the peak throughput of the GPU, known in like theoretical terms. So we know what the peak memory bandwidth of the GPU is, and we know what the peak compute throughput of the GPU is, right? These are just kind of hardwired things baked into whatever the GPU is. So like we know that on this A100 GPU that I'm running on today, that the memory bandwidth is about 1500 gigabytes a second, and that the peak compute throughput, well, it depends on what kind of compute we're doing, right? In this case, we're primarily doing FP64 math. So we're comparing against the 9.5 teraflops per second that this GPU can do double precision, like FMA math. And so the way it summarizes this information as kind of the top level statistics are really 3 numbers that you want to look at. First, of course, you want to look at the duration, right? The duration is just how long it took that kernel to run. And this kernel runs in about 43.5 milliseconds. And then you want to look at these 2 rows, memory percent and then SM percent. So memory percent is the percentage of peak memory throughput that you achieved for the memory subsystem that is the most important limiter to the performance of your kernel. So there's obviously several memory subsystems on a GPU. There's the main RAM, and then there's the caches. So any one of those 3 could be the primary determinant of your performance, and then, or the most important limiter of the 3 to your performance. And so this memory percentage will tell you what percentage of that subsystem you achieved. And then if you want to know which of the 3 subsystems, how it breaks down, you can then look at speed of light DRAM, which is just the high bandwidth memory, the main RAM, speed of light L1 cache, and then speed of light L2 cache. And usually, but not always, but usually the memory percentage number is one of these 3, because it's just picking the one that is the most relevant determinant for your kernel. So we can see that this 0.36% for memory percentage corresponds in this kernel's case to the DRAM number, right? So it's saying we're getting only 0.36% of peak memory throughput, and for the memory aspect of this kernel, the thing that really limited us was DRAM. Now, it also tells us that SM percentage is 99.85%, right? SM, or streaming multiprocessor, are just the individual compute units on the GPU. These are our fundamental unit of compute. And this is a measure of what percentage of peak SM throughput we got. Now, notice that we're just getting a number. And so what it does, kind of like with the memory subsystem, is it looks at all of the different modes of computation that you do. And then it says, of all of the compute pipelines that we're using, where pipeline is a generic, just like floating point math or integer math or something like that. I look at all of the compute pipelines and ask the question, of the one that is most heavily used and is the one that is limiting my performance, what percentage of that subsystem am I getting? And this tells me that whatever it is, I'm getting almost 100% of that subsystem. So that's really good, right? This is saying that for this kernel, we could declare I am compute bound, right? I am basically getting 100% of the compute throughput of the GPU. And so the only way that I could get faster is either A, change the kernel, or B, buy a faster GPU, right, that has more SMs. But barring one of those two things, I'm basically done. There's no way that this kernel can get any faster. Notice that I've said all of these things without even showing you the code or even knowing anything about this kernel. Well, obviously I know something about this kernel because I wrote this, but we haven't talked about the code yet, right? We're just looking at what is the tool saying about this kernel, right? And so we can answer that kind of question without even knowing what the code says, but we will look at the code. Then you get this launch statistics section, which gives you some summary information on like how many threads and blocks were used to launch this kernel. Now I know that not all of you are CUDA programmers, but you know, hopefully you understand that regardless of how you write to targeted NVIDIA GPU, at the end of the day, all goes through the same process where you're basically generating CUDA kernels. And that's true regardless of whether you're using OpenACC or OpenMP upload, or like if you use Cocos is also generating CUDA kernels. And so we can think about it in the same way and answer basic questions like, does this GPU have enough work to saturate, or does the kernel have enough work to saturate the GPU, for example? And then the occupancy section here tells you a little bit about occupancy. And so I will come more into this in a little bit, but I just wanted to make the point that you usually start with the GPU speed of light section, and then there are other sections that are available if you want to know more about what's going on in your kernel. And usually you would refer to the other sections when you're not getting 100% of one of these things, so you can better understand what your limiter to performance actually is. Now, you can, by default, when you load the tool, it does these three analysis sections: GPU speed of light, launch statistics, and occupancy. There are more kinds of analysis that the tool can do. And so if you do -- set detailed, what that does is it collects more information about your kernels. A consequence of requiring more information is that it's more expensive to process the kernel. In general, the way that Nsight Compute works is that it has to be able to rerun or replay your kernel multiple times in order to collect all the statistics that are needed to generate this kind of analysis, because just due to the limits of how NVIDIA GPUs are designed, we cannot get like an infinitely large number or an arbitrarily large number of performance counters all in one run of your kernel. So we'll re-execute your kernel multiple times, and then how many times depends on how much analysis data we're trying to collect. But you can see that we now get more information from the tool because I added this -- set detailed. So let's scroll up to the top and so a couple new things. First, we get this compute workload analysis section, we get this memory workload analysis section, Scholar statistics. So there's a bunch of new sections, and these can be helpful for understanding performance. Now I'm going to stop here with the standard out and then jump to the user interface, because I just think that's more fun and prettier. But do know that a lot of this information is available at the command line. So if I want to get this information and load it up into the user interface, the main thing I need to do is pipe this to an output file. So I'll just call it the same thing. And then what I'll need to do is copy this file down to my local computer and then load it up into the user interface. Of course, if you have like, X forwarding or like no machine set up at NERSC, you can load the UI if you want to. The name of the UI is NCU-UI. But that's not going to be pleasant given the setup that I currently have on Theta GPU. So I'm just going to go ahead and copy this file down to my system. The tool helpfully printed out the name of the file that was generated. It's the name I gave it, and then the file extension is .ncu-rep. And so then I'm going to go ahead and copy that down to my system. That didn't work. Why didn't that work? What did I do?
Max, Alfred is asking if there is any documentation. I believe NVIDIA has a lot of documentation for Nsight analysis?
Yes. So first of all, I will say that even though I called this roofline analysis is one of only several aspects of what Nsight Compute can do. And there's a fair amount of documentation on our on the web page, the Nsight Compute documentations. Let's see if we can find that. If you go to the Nsight Compute documentation, this is broken up into several sections. There's a section on the CLI, a section on the tool, and then this kernel profiling guide section. And the kernel profiling guide tells you a little bit about the different sections. I'll just link this for you so you can look at it. And so, for example, there is a section here on the roofline charts, and it explains a little bit about how we think about this GPU speed of light section. I'm going to go through and talk about this in a moment, but this is here in the documentation if you want to take a look. Okay, I was going back to figuring out why this didn't work like it did an hour ago. Maybe I have this like symlink or something that's not following the symlink. Yeah, okay, that worked. Okay, so I have Nsight Compute open. It's obviously pretty boring when you load it up and you haven't loaded a file. So you generally, if you have an NCU-rep file, you would go to File and then Open File and then locate that on your file system. Let me see if I can find this. So I called this kernel ABC. Okay. So basically what this does, if you load up in the user interface, is then just show you the same information that you were getting in standard out, but in this user interface form. So the information is laid out in the same way. So if you were to collapse things, you would see sections listed one by one. So the GPU speed of light section, the compute workload analysis, memory workload analysis, et cetera. And our general workflow is you start with the speed of light section, and you understand what your high level performance limiter is. And then you would consult one of the other sections if you need more information. So this shows us a bar chart of the two pieces of information that we were just looking at, the SM throughput and the memory throughput. And the SM throughput is 99.9%, so it's pretty good. And usually we could stop there. Now, if we were to plot this on a roofline chart, it might look like the following. So in a roofline chart, what you do is you plot the floating point throughput in like flops per second on the vertical axis, and then you plot the arithmetic intensity on the horizontal axis. So the arithmetic intensity is the number of flops you do divided by the number of bytes moved. And so this kernel has an arithmetic intensity of 677. And you can know that by hovering over the dot that occurs on the plot. So the dot is what this kernel actually achieved. And so this has an arithmetic intensity of 677 and a throughput of, it looks like 3.77 teraflops per second. And so we also plot on this plot the theoretical limits for the GPU. And if the arithmetic intensity is low, so you don't do that much floating point work per memory instruction, we are in the memory bandwidth bound part of the plot, and that's over here. And then if we do a lot of flops per byte moved, then we're compute bound and we're over here. There are two roofs that are relevant here. And the reason we plot two is that both single and double precision math could be relevant for your kernel. So we plot the double precision roofline and the single precision roofline. And so you would compare the thing you achieve to the thing that the math that you're doing. This kernel only does double precision math. And so the relevant thing to compare to is the peak theoretical throughput in double precision. So this is telling us that what the peak throughput is for this kernel, and then what we actually achieved. So basically we're getting something like half, right? We're getting half of the peak compute throughput of the GPU. And so this tells us, could we do better? Could we get a higher peak throughput out of the GPU? The answer is yes, right? We haven't fully saturated what the GPU can do. And because we're clearly in the compute bound part of this plot, we are relatively at leisure to make transformations that could move us upward, and we would still be compute bound, and still probably for this kernel, no matter what we do to improve it, we're still going to be compute bound. And so it's very plausible that if we could change something about this kernel to, for example, use more efficient instructions or something, we'd have to analyze the code, but there's potentially things that we could do to move things up to the roofline. The whole point of the roofline is that you couldn't get any higher than the roofline, but at least this gives us a sense of what fraction of peak are we getting. Okay. Now, there's a drop-down menu that is available in Nsight Compute, and that drop-down menu includes a list of all of the kernel launches. So we've just been looking at kernel A so far. Let's look at kernel B. So there's a question in the chat about what is the maximum upper bound of computational intensity? So we're defining arithmetic intensity as number of flops per byte. And so normally the way you would do this calculation is you would look at your kernel and you would calculate the both the number of flops done and the memory operations done. So in fact, let's go ahead and look at that for kernel A. We haven't even looked at the code yet, so let's take a look at it. This is an example codes, kernel abc.cu. So here's kernel A. Kernel A, this is a standard CUDA kernel, nothing special about this. What it does is it computes the normal thread index in CUDA. So you get a thread for every, you get one index for every thread launched. You're operating on an array A, and then we're basically just assigning something to a double precision array A. We're just assigning a number D to that array. And the way that we're computing this value D is we're basically doing this really stupid, completely arbitrary calculation where we say from J equals 0 to J less than M, we add D plus equals A of index. So basically we're just multiplying A of index by, a factor of M, and then setting that same value back to A. Completely arbitrary calculation, doesn't really mean anything, but it's a way to generate like a lot of flops for free. This pragma unroll statement just means that we want to make sure that there's a lot of flops involved. So this will just be a long sequence of arithmetic statements and then some memory operations. And so the way that we can compute the arithmetic intensity of this kernel is we can look at how many memory operations are done and how many floating point operations are done. So how many memory operations are done? Well, I claim that a well-written compiler will notice that the right-hand side of this expression is identical for every element. It doesn't depend on J, right? And so what we can do in this case is copy the value of A of index to a register, and then we can just add that register to D M times. Now I've chosen M to be a runtime variable here so that the compiler cannot just optimize this out by like calculating what M is. And I verified that in fact, it's not optimizing this out. It really is doing M, plus equal statements in a row. And so there's just basically one read of A of index and then one write to A of index. So there are two memory operations in this kernel per thread. This is a double precision number. And so we know that there are 8 bytes associated with it. And so then the number of bytes moved in this kernel is 16 bytes per thread. So that's our denominator. The numerator is how many floating point operations there are. Well, we can just read that out, right? Basically it's M, right? There are M floating point operations in this kernel. And so every time for every loop index for J, we're just doing a single floating point operation, D equals D plus A. That's what we're doing. And so the arithmetic intensity of this kernel is M over 16. And the larger M is, the more of these arithmetic operations that we do, the more work, the higher the arithmetic intensity will be. So then to go back to this question of, well, what is the upper limit? It could be arbitrarily large, right? Because we can make M arbitrarily big, and then we are doing more and more work. And so the way to think about arithmetic intensity is, given that we had to load in some data from memory, how much work were we able to do on that piece of memory before we had to return it? And the reason this is an important calculation on any modern high-end HPC processor is that, generally speaking, to be very rough, memory is more expensive than compute in the sense that it takes many, many cycles to read in data from memory and relatively fewer cycles to compute on that data. So the more compute operations that we can do, having read some data in from memory, the more we will amortize out the long cost of having read in memory from DRAM. You can take a look at this code and see how I launched this configuration. That shows m equals 10,000. And so the arithmetic intensity of this kernel is 10,000 over 16. And that just happens to be about equal to this. It's pretty close to that 676 or whatever we got. So this is a compute bound kernel, and it's limited by compute. And so we expect it to be, right? We're doing a heck of a lot of flops here, and that's what the profiler showed us. Question in chat, how do GPU registers work? Are there some registers per SM or per core? Okay, so GPUs, kind of like CPUs, but this is a little bit different in how they work, have a register file per SM. And so, you know, the notion of a core in thinking about GPUs can be misleading because some people might claim that the floating point math unit on an SM is a core. Other people might claim that the SM itself is a core. You know, there's no well-defined terminology for what a core is. And so one could have an argument. I don't think it would be a very interesting argument about it. But the point is, there is a register file per SM. And then every thread has some number of registers associated with it. And then they have to share the same register file. And so there is a constraint then where if your kernel uses too many registers per thread, you could hit a limit because there just aren't enough total registers for the entire SM to fit. In this case, we're using relatively few registers per kernel. And so we have no concern. We have enough registers in the SM to fit every register from every thread. But this is a concern when you have hungry kernels that require lots of registers. There can be constraints then. You may not be able to run as many threads because of the limit on constraint and the size of the register file. Okay, isn't there a pipeline delay exposed in kernel A because of the recurrence? Well, yes, and in fact, if you look at the code here and then compare it to the output, we don't get like exactly what the theoretical result would be. So asymptotically, this looks kind of similar to that naive calculation I just said. In practice, it's a little bit different from that. And it is true that the actual details of how we would execute a large number of floating point operations in a row like this are a little bit more complicated than what I just said. But for the kind of high level analysis that we're trying to do right now, I'm kind of eliding over those details. Okay. My kernel is all integer operations. Is there equivalent output for IOPS? Well, in the tool, we don't expose this. Like we don't have a roofline chart for integer ops. However, it is straightforward to make one because it uses the same, well, hold on. It can be straightforward to make one because it uses the same kind of construct. One reason why it's a little bit subtle for integer operations is just a difference in how we can count flops and integer ops in kernels. So I spent some time working on this with NERSC a while ago, and I believe, I'm not sure if it's in this repo, but I believe I came up with did I come up with that? I don't know if I published it here, but I spent some time working on a roofline chart for integer math, and there were some subtleties with it. So we didn't yet put this in the tool because we can talk about this offline if you want to know the ugly details. It turns out it's a little bit more complicated than with the floating point ops to like uniquely define what the integer roofline chart should look like. But the nice thing about Nsight Compute is that you can define any sort of section that you want. And so it's possible to create your own integer roofline chart, and you can talk to me offline if you want to know how to do that. And then I can give you the appropriate caveats about how to trust it. Oh, and thank you, Moaz, for sharing what you did. How do I select a particular kernel to analyze? What if it's a templated kernel? How do I select one particular version? So that's a good question, and I probably should have said this before. You know, when you do NCU like we did, we are selecting every kernel, and so that can be a disaster if you have many kernels, but only like a few that you care about. And so what you can do is there are some flags you can use in Nsight Compute to control which kernels are profiled. If you do ncu-help, then it will show you what your controls are. And pretty simply, the highest level one to start with is this -- kernel regex or kernel name argument, or just -k for simplicity. And so quite simply, the easiest way to do it is just do -k and then the name of the kernel, right? So I can do -k and then kernel A. And then this will say only profile kernels which match the regular expression or exactly match the name kernel A. So you'll see that this should only profile kernel A, but it did not profile kernel B or kernel C. Now, if you use the longer form, or rather, if you do kernel name and then regex : and then a name, then you can choose some regular expression to match. And then if you use -- kernel regex base, you can choose whether you want to be looking at like the mangled or demangled kernel name or function, which would elide the templated distinction. And so you can use these options to control how you're matching. So it should be possible to distinguish templated kernels this way. Okay. All right, let's continue on. So let's look at now kernel B. So kernel B is actually the exact same kernel as kernel A, but turns out it gets a little bit different performance. So kernel B only gets an SM percentage of 32.5% instead of the 99.9, right? And so if we look at this code, it's exactly the same code, I promise you. So if we got different performance between kernel B and kernel A, the only explanation could be that its launch configuration was different. And in fact, that is what I did here. Kernel A just launches 64 threads per block and then picks enough blocks to fully spread over the size of my array A. What kernel B does is intentionally ruins the performance is the wrong term, but basically I'm intentionally changing the launch configuration of this kernel by choosing to use a large amount of shared memory, dynamic shared memory per kernel launch. If you're not a CUDA programmer, don't worry about it too much. Just know that this is basically allocating a large amount of user-managed opt-in cache for each thread block in the kernel. And so this, in fact, the number that I'm choosing here is the maximum that you can choose on the V100 GPU. I'm running on A100 here today, but I wanted this code to be useful for both the V100 and A100. And so this basically severely limits how many concurrent thread blocks can be running on each SM. And so even though I didn't change the code at all, I have now changed the runtime characteristics of this kernel. And in particular, I changed it enough that I no longer am achieving 100% or nearly 100% of peak throughput. I'm only achieving 32.5. So now that I'm not achieving 100%, now it would be fair to ask, what could potentially be a cause of this, right? And if I look at the roofline, and I look at my roofline .now, I'm now only getting 1.2 teraflops instead of 3.5, right? So basically I'm getting about a third of the performance. And that actually kind of matches this, right? Where I was getting like a third of the 100% of SM throughput that I was getting before. Now in Nsight Compute, what you can do is click this add baseline functionality if you want to. And what this does is it sets kernel A to be like a baseline performance measurement, and then kernel B, when I switch over to it, can then be compared to kernel A. And so it will give me my current kernel, the one I'm looking at now, and then the characteristics of my baseline. And I will rename this baseline kernel A just so we don't forget. Oh, I'll try to, if I type correctly. Kernel A. Okay, so the blue here is the new kernel B, and green, you can see that color distinction, is the old kernel. So clearly there's a big drop here. We went from like 100% SM throughput to 32. Okay, so in some cases, we have like an expert system in the tool that will attempt to give you some analysis about how to look for performance bottlenecks. You know, like any expert system, it's not going to be perfect. It may not always give you super useful information, but sometimes it can be useful when you're first using the tool to look at it. And so it'll tell you here that your bottleneck is this kernel exhibits low compute throughput and memory bandwidth utilization relative to the peak performance of this device. Achieve compute throughput and or memory bandwidth below 60% of peak typically indicate latency issues. So this gets back to our understanding of how a GPU works, right? GPUs have generally long latency for instructions compared to CPUs. And so the way that we optimize on a GPU is by having many instructions running concurrently with the hope that we can hide the latency of any one instruction with some other work that's going on. So if we are getting less than 60% of peak, 60% is kind of like an arbitrary number, but it's like a reasonable threshold, right? It's right in the right ballpark. If we're getting much less than 60% of peak, then often what this indicates is that we're not launching enough parallel work to hide the long latency of individual operations. And so that's what this bottleneck analysis is telling us here. Of course, this happens in lots of HPC codes that you don't hit 60% of peak. And so just saying that you are hitting latency issues is a generic statement. We're generally going to have to dig in to understand more, but that at least gives us a place to start looking, right? We're not launching enough parallel work to hide the latency of individual operations. And so we want to ask the question, why are we exposed to this latency? It will tell us to look at scheduler statistics and warp state statistics for potential reasons. And so we could do that if we wanted to. Scheduler statistics tells us information about how many warps are active on the GPU. So the warp, you may know from your understanding of GPU, is a group of threads that execute in parallel. They do, a group of 32 threads on NVIDIA GPU executes an instruction in parallel, and at any given clock cycle, we're issuing a given warp's instruction. And so we want to maximize the percentage of a warp that is doing the same thing, or the percentage of threads in a block that are doing the same thing, so we can have as large a active thread ratio as possible. And B, we want to have as many warps as we can. The more warps that we have, the more parallel instructions we've got going, and so therefore the better the latency hiding ability is. Let me clear the baseline so that this becomes a little bit easier to see. So we're just looking at kernel B now. And what we're saying is that the maximum number of warps per scheduler on an SM is 16, but theoretical warps for this kernel, right, given the constraints of this kernel, I can only actually have 1 warp per scheduler on the SM. And so there's a huge gap between how many the GPU hardware will support and how many this particular kernel will support. And so immediately I'm giving up a factor of 16x in terms of how many parallel instructions I can have going at one time. So this is a pretty obvious clue, right? It's saying we just aren't launching that many warps in parallel. And so our latency hiding ability is now it's harder to achieve. And when that's true, you typically want to look at the occupancy section. And the occupancy section basically tells you, and occupancy is another measure of that same kind of thing. Occupancy is a measure of the number of warps that are actually active on the GPU versus the theoretical maximum number of warps. And so this tells us that the theoretical occupancy of this kernel is 3.12%, which means given what we know, how many warps in SM can be running according to the hardware constraints, how many can this kernel actually run? And the answer is a maximum of 3% of that peak, which is just basically that 1/16 factor that we were just looking at. And so that's a pretty big clue here. If you have a theoretical occupancy of 3.125%, this is telling you basically that you are severely constrained on how much performance you can achieve on the GPU. Despite that, we're getting okay performance, right? We're actually getting a third of the peak compute throughput of the GPU, despite the fact that we are launching only 1/16 of the warps that we could be. So this is, a consequence of this being a pretty extreme kernel. But even for this kernel, which is only doing floating point math, right? This is showing us we're just not launching enough work to fully saturate the compute throughput of the GPU. Okay. Let's look at kernel C. Oh, and sorry, I didn't fully explain this point, but the reason why is because of this shared memory constraint, right? We are launching a large amount of dynamic shared memory per kernel, and that limits the number of blocks that can be simultaneously resident on the SM. And the reason is that there's a finite amount of shared memory in hardware per SM, and blocks have to share that. And so the more shared memory a block uses, the fewer blocks there can be per SM. And this block limit section here on the occupancy area tells us, summarizes for each of the possible constraints that determine how many blocks can be running simultaneously on an SM, what is the constraint for each of these characteristics. And so this breaks down into block limit registers, block limit shared mem, warps are the main ones to look at. And also SM. So this last one is not usually that important. This basically tells us like how many warps can the SM actually fit like in hardware? And the answer is 32 for this configuration. What we typically want to do is look at the lowest number. The lowest number among all of these three of these numbers is the one that determines how many blocks can be simultaneously resident on the SM. And what we see here is that the number is 1 for shared memory. And so this means that we can only be running 1 block per SM because of the shared memory usage of the kernel. And that goes back to this point about how much shared memory was used in this kernel. We can only fit 1 block per SM. And so that means we are severely limited in how much parallelism we can get. And so that's the ultimate constraint here. Feel free to jump in with questions as I'm going. I'm just gonna.
Ναι. Στα σήκωσα ήδη.
Okay, that appears to be somebody who's not muted. How do I analyze a kernel running a particular data set chosen via the command line? What if I need to skip over some start at the beginning of the application? Yes, so I should have said that too. So I answered the question about how to select which kernels to profile. I did not answer the question about, or the full answer to this question. So we have other constraints as well. In addition to selecting which kernel names that we want to profile, we can also choose how many kernels we want to profile, how many kernel invocations we want to profile with -c, and then, or -- launch count. And so this says, like, if I did -c10, then this means I only want to profile 10 kernel invocations. And NsightCompute will treat each kernel launch as a separate activity, and it will profile every single kernel launch independently. And so this tells us how many kernel launches to profile. -s or -- launch skip is how many kernel invocations we want to skip before starting profiling. And so this can be used for skipping through warm up on the application, and that's a pretty common thing to want to do. I see the unified L1 shared memory is 192 kilobytes on A100. The shared memory set is 96 kilobytes. Why is the maximum reported 1, not 2? Even though the size of the unified L1 shared cache in A100 is in fact 192 kilobytes, we cannot dedicate the entirety of that hardware to a single large shared memory configuration. On pretty much every GPU, we have to ensure that there's at least some amount of memory there for L1 cache, because there's basically not any kernel where we couldn't have 0 L1 cache. And so we usually, on recent GPU generations, limit the size of the largest shared memory configuration to be about 32 kilobytes less than the total size. And so on A100, you can do 192 kilobytes minus 32, so like the largest shared size is 160. And then on V100, you could do 96, even though the size of the unified L1 shared cache was 128 kilobytes. Okay, so one more kernel to look at is kernel C. And I'll go through this rather quickly because we are almost at the end of this time session. So kernel C let's just first look at what we get, and then I'll show you the code. So kernel C is rather different. Kernel C is memory bandwidth bound, and it achieves 90%, a little bit over 90% of peak memory throughput. If we look at these speed of light numbers, right, it says SOL memory is 90.64%. And what I told you is that usually you want to look at which of the three memory subsystems is the one contributing to that. So we get a breakdown for L1 cache, L2 cache, and DRAM on this GPU. And if we look at the three numbers, we see that L2 cache matches exactly the SOL memory number. And so we can pretty confidently conclude that in this case, L2 cache is the limiter for the performance of this kernel. This is a memory bandwidth bound kernel. Definitely we're going to need to think about it, put a different lens on for understanding this kernel. If we look at the roofline chart, we are now in the memory bound part of the roofline. And so if we put our hover our dot over it, we see an arithmetic intensity of 0.07 flops per byte. So we're just not doing that much math per memory operation. That's more typical of a HPC kernel than the last one I showed. And we're only getting a performance of 65 gigaflops, right? So this is like pretty tiny compared to the peak throughput of the GPU. Okay, so what does this kernel look like? Here's kernel C. Kernel C, and you can study this on your own if you want to, but basically it's adding, it's basically copying one array to another and doing A of index equals B of strided index plus B of strided index. So it's basically doing one floating point operation, an add, and then storing that to an element A. So there's not that much math here to compensate for the memory movement. But the access into B, as you can guess from the name of this index, is strided. So while A is indexing just consecutive elements, we're just accessing consecutive elements of A. So this is a nicely coalesced access to A. B is a little bit different. B has some striding to it. And the math here is kind of convoluted. But basically the way it works out is that for a given warp, we're accessing memory locations that are a size stride away from each other. So like the threads in warp 0 access element 0, stride, 2 times stride. The threads in warp 1 will access element 1, element stride plus 1, element 2 times stride plus 1, etc. There's a wide gap in memory locations on the accesses to B. The size of the stride is 16. I've just chosen that arbitrarily. So we can guess, knowing what we know about GPUs, that this will be an uncoalesced memory access, and therefore is going to not get anywhere. It's going to be a suboptimal access pattern, right? And if we knew what we know about GPU performance, then we would expect that this kernel would actually not get a good fraction of memory bandwidth, because we know that uncoalesced memory access patterns are poor. However, if we look at the output of this profile, we actually get a slightly different story, right? It's telling us, allegedly, it's telling us that we're getting 90% of the peak throughput of the memory subsystem. But this is when you got to be careful, because what it's telling us actually is just, given the memory subsystems that are on the GPU, and you're issuing some memory operations, what percentage of the peak throughput of that subsystem did I get? This is not like a normative statement, right? Getting 90% of something isn't necessarily good. It's just a fact about your kernel. So what this is telling you is we are getting 90% of the peak throughput of L2 cache operations, but we need to combine that with our knowledge as programmers to think about, is that a good thing or is that a bad thing? Well, if we look at this kernel, we should be able to conclude that this is a bad thing that is happening, because this kernel is copying from global memory this array B to this other array in global memory A. And so as a result, we want this kernel, like an optimal kernel that does this kind of operation, should be limited by DRAM bandwidth. And yet this actual kernel that we wrote is limited by L2 cache bandwidth. And so the fact that we are limited by L2 cache bandwidth is a smoking gun that, like, this is not an optimal way to do this A equals 2 times B kind of thing, right? Whatever we're doing doesn't really map well to the GPU architecture. And as a result, we are hitting L2 cache very heavily instead of hitting DRAM heavily. Now, this does not mean that DRAM is unimportant to the performance of your kernel, right? It just means that if we made DRAM like 10% faster, that would not actually change the throughput of your kernel, because what is limiting us here is not DRAM bandwidth like we'd like it to be. What's limiting us here is the heavy pressure we're putting on L2 cache. Why are we putting pressure on L2 cache? Well, we can know this by thinking about what we know as a programmer, because we know that we are basically pulling in large amounts of data per every thread, but most of those array elements are being unused for any given thread. However, some other work may be able to reuse that data that got pulled into L2 cache. And so there will be a large amount of contention for L2 cache pulling in this data that's kind of making up for the uncoalesced excesses. And so that will help you understand what's going on here. So I think I'm gonna stop there as kind of my introduction to how to use the tool, because I've already gone on for about an hour now. If you want to stick around for the kind of next half hour, I can talk you through this example that we have that goes through the Berkeley GW kernel, and say a little bit about that. But I did want to close there and let people know if there are any other last minute questions about how to use Nsight Compute. Okay, don't hear any questions. Yasi, I don't know, should we continue recording for the kind of hands-on portion, or should we stop that there?
So we can go until like 12:30 in our time, or 30 minutes longer. So because we scheduled it for 90 minutes. So if anyone wants to continue, they can, if you are available.
Yeah, I'm gonna keep going. I just wanted to make sure that people know that if they leave now, it's okay. You got the main thing that I want to talk about, how about use the tool. And now I wanted to give people an opportunity to try this example code and say a little bit about what it does. So in this example code, this is using, oh, you know what, since, let me just finish up my thought on this kernel C before I do that. So with kernel C, what we were saying is that we were hitting L2 cache pretty hard. And when this is the case, when we're memory bandwidth bound, right, we want to think about, well, can the tool tell us anything about what we did wrong here? Well, actually, yes, because we know that we're memory bandwidth bound. And so the logical thing to look at here would be the memory workload analysis section. So if we look at memory workload analysis, it tells us some information. It tells us the achieved memory throughput. It tells us the hit rate of L1 and L2 cache, and then some more information. But we actually did not quite collect enough information here to give us the full memory workload analysis. We can get a more detailed understanding of this memory workload. And the thing we need to do is just collect a little bit more information. So what we're going to do now is do --set full. So --set full means I want you to collect everything that you can about this kernel. So throw the whole kitchen sink at it, and then collect all of the information. And so that's necessary for the full set of sections that Nsight Compute knows about. And Nsight Compute will then do this memory workload analysis section and one or two other things that we could talk about if you want to. But you can see it now adds more work. So now we had to do 33 invocations of this kernel. So it's more expensive to collect, but we also get more powerful analysis. Then what I need to do is just copy this file down to my system. Make sure I'm going to be overwriting the file. Okay. Let's go ahead and open up the new report file with the full set of information. Okay, so now I should be able to use this memory workload.
That you need to see this video. Today, you're about.
Oh, somebody's got mute. Okay. So now we can expand this memory workload analysis section, and this gives us a nice little memory chart. And this memory chart shows us quite a wealth of information, and it would take some time to walk through all of it. And you can consult that documentation that I linked before to get a little bit more into this. But it basically breaks down a chart of two different kinds of information. On the left side of the chart are logical memory spaces that exist on the GPU and instructions executed to memory instructions executed among those spaces. So basically, here's the kernel, and it's saying, look, you know that there are logical memory spaces on the GPU. Global memory is the logical memory space that ultimately points back to DRAM, and that's where like our main arrays live. Local memory is per thread stack memory. Shared memory, we know about from studying CUDA. There's a couple other things, texture and surface memory, that aren't really used that much by HPC programmers. So global, local, and shared are typically the ones we care about most. And it shows us how many memory instructions were executed to global memory. And then on the right side of the chart, it shows us physical memory spaces, hardware on the GPU, L1 cache, L2 cache, and then if you go up further, device memory, which is DRAM, system memory, which is host CPU memory, and peer memory, which is any other GPUs on the system connected, for example, via NVLink. And so it shows us movement between these physical memory spaces, as well as requests from global memory to L1 cache. And so, for example, we can see how many memory instructions were made between that global memory instructions, which then ended up percolating down to L1 cache, and then to L2 cache, and then device memory. So that's a pretty standard way of issuing instructions, right? We ask for some global memory, and then we ask, is it an L1 cache? If it's there, we get it. If it's not an L1 cache, we go up to L2 cache, and then if it's not an L2 cache, we fall back to device memory. And then we can see how much data moved in between these spaces. And if you wanted to, you could compare this 125 megabytes to the theoretical size of the arrays. That would be an instructive thing to do, and you can do that in your own time if you want to. But this will help us understand, in many cases, what's going on in the memory subsystem. And then the other thing that you can do is that you can think about this in terms of this kernel in terms of coalesced access patterns, right? So the way to think about this kernel is how much memory did we move compared to how much data we theoretically could have moved in like an optimal version of this kernel. And so if we look at this kernel, it may be instructive to us to do those kinds of calculations that I was mentioning. So the size of the array is 80 times 2048 times 100. You can see that I sized this for E100, even though I'm running on A100 in this case. And so we could do a calculation to understand the size of the data. In fact, let's go ahead and do that. So 80 times 2048 times 100 is the length of my array, so about 16 million. If we look at what this kernel is doing, it's basically copying an array. It's taking an array, multiplying it by 2, and then writing the result to A. And so we can calculate how many memory, how many bytes should be moved, right? We can think about this in terms of, well, I know how many bytes are written to A, and I can think about this in terms of how many blocks and threads were launched. So if I look at the configuration, I'm launching num blocks and threads per block. And so the number of threads per block is 64, and the number of blocks is just n over 64. And so we're launching enough work to fill out the GPU. So every element of A and every element of B is being copied. It's just it's a little bit different how it works, because with A, we're just consecutively running through the array. Whereas with B, we're kind of staggering the threads. So every element of B is being accessed, but threads from each warp are kind of moving out, striding along the array and copying data. So then if I take the length of the array and I multiply it by the size of the number of bytes per operation, this gives me a sense of what the total amount of data I should be moving is for this kernel. And so you can use that to compare to what you actually achieve. Now, the thing that you want to be looking at for this kernel is how many bytes are we moving compared to how many we theoretically could move. And if we know how coalesced accesses work on a GPU, then you may know that the ideal operation is that we move all of the bytes in one cache line, that threads in the warp access some number of cache lines, And ideally, we use as many bytes from each cache line that we pull in as possible. So a cache line on a GPU, on a NVIDIA GPU, is 128 bytes. And so we want to be using as many of the 128 bytes as possible. But we know that we're not doing that here. When we access B, we are pulling in elements 0 and then stride. The stride is 16, and the size of a double is 8 bytes. And so we're accessing elements that are 128 bytes apart when it comes to array B. And that means then that every cache line that is being pulled in by this warp is only using 8 of the 128 bytes. We're reading in the first double from that cache line and then ignoring all of the other doubles in that cache line. So we're basically getting a very small fraction of peak throughput, or peak usage, or peak efficiency, I guess you would say, of these cache accesses. And the fact that we pulled in a lot of data is why L2 cache ends up being hit so heavily, because that data that we pulled in that cache line could be used by warp 1, right? So warp 1 does need bytes 9 through 16 of this data, or 8 through 15, I guess, of that cache line, and so it will happily take advantage of it, but it's not as optimal as it could be. And so then you can, if you want to compare this, when we look at the kernel, you want to look at information such as sectors per request and total number of sectors moved and requests. So if we look at kernel C, that's what we want to be looking at is sectors per request. Like, that's the way to think about it. So a sector is a 32-byte chunk of DRAM. And this gives us some sense of, like, per memory request, how many of these sectors are we moving in? And it gets a little bit complicated to, like, calculate this. But if you just want to jump to the the final resolution of this analysis, it's that the tool can calculate how many sectors could have been moved in, like, an ideal version of this kernel, and how many were actually moved. And it will compute the ratio of those two things. And so if you look at the bottom of this profile, it will tell you uncoalesced global accesses, expected some number of sectors, got some other number of sectors, and then gives you the ratio of those two. So in other words, the optimal version of this kernel would have used 4x fewer sectors than the one that we actually did. And so this corresponds to the fact that we are moving many more elements of memory than we need to perform this operation. And so this is just the shortcut, but you can also, if you want to, dig into this in more detail here, and it will, like, show you that the sectors per request number is 1, where ideally it would be like a large number like 4. And that's what you would get for a coalesced access. Okay, so that's the walkthrough of kernel C. And then I just want to introduce this Berkeley GW kernel example, and then let you try it out on your own if you want to. So this kernel is actually pretty simple. So it's an example code GPP, and then the source file is called gpp.f90. So again, it's Fortran file, and we've chosen to parallelize this operation in OpenACC. This code is, there's only one loop that we care about in this code, and it's just a simple nested loop. There are 4 loops in this nest. You can see that there are 4 different variables: N1 loc, IGP, IG, and IW. These are, like, the names of these variables as they exist in Berkeley GW. So this is realistic code with all of its, warts, where it means we're not going to immediately understand everything that's going on here. But basically, this is just a large nested loop. It does a bunch of work. It performs a reduction. You can see that here. Even if you're not super familiar with OpenACC, you can probably guess what's going on here, right? It's like reducing, it's adding, every thread is adding to these 4 variables that have these names here. OpenACC is collapsing these 3 loops into one loop, and then I'm just performing this loop sequentially. This loop has a trip count of 2, which I've put here in with a comment. And so it'll just perform everything in this section of code sequentially per thread, distribute these outer 3 loops among all threads, and then it'll just do that. And this is basically the only bit of work for this kernel. The fundamental unit of compute here, these are double precision complex numbers. And so you can take a look at this if you want to, but we're basically working with double precision complex numbers here. That's because that's what Berkeley GW does. And so that's what this math does. It's like, you can see there's not that many instructions here, but I'm not even sure I could explain to you like what calculation this is actually doing. I don't really understand the science of it myself. I would just treat this as a computational scientist and just think about, just analyze the computational pattern of this kernel. So there's like some arithmetic, some reading into memory, there's a couple of conditionals here, and then there's this reduction at the end. So you can go ahead and study it on your own time if you want to. But what we've done for this kernel is ask you to use Nsight Compute to analyze it. And this is intentionally challenging because it's a relatively complex kernel. It's one you've never looked at before. And so it tests your ability to look at a brand new kernel and see if you can use the tool to help you figure out what's going on. If you go into this GPP directory, you can type make to build it. This just uses our NV Fortran compiler to build. And then the name of the executable that gets generated is gpp.x. So if you just run it, what it does is it runs this kernel and it tells you how long it took to run. And then also it does a simple correctness check to verify that the answer is correct. Now, let me make sure I didn't, yeah, okay. So this is clean repository. And then if you want to profile it, what you can do is, like we learned before, you can just do NCU and then -o, let's say GPP original is what I'll call it, and then go ahead and collect it. Now, because this kernel like takes of order 1 second to run, this means that it gets pretty expensive to run through it with Nsight Compute, because we have to run this kernel multiple times. And how many times is variable depending on how much we ask for. In this case, we need to do 10 passes. And so it's like increasing the runtime of this application by a factor of 10. And it could be even worse if we do collect more information. So be aware that that's a cost. This does tend to take a bit of time. I can then bring this down to my system. And I can load it up into the tool. So GPP original. Okay, so let's see. This kernel uses 74% of peak compute throughput and 23% of peak memory throughput. So already this is actually a compute bound kernel. That's where this starts. So that's interesting. It's not as common in HPC to immediately start with something that is compute bound like this, but this is an example of that. You can see there's a fair amount of arithmetic here. So it's not necessarily super surprising, but actually calculating this would be challenging, right? Like it would be tedious to count the memory accesses in this kernel and then generate a like an estimate of arithmetic intensity. So what you can do is, if you want to have it do roofline analysis, so that's where this -- set detailed comes from. That adds the, what do I do? Oh, I need a -f. This -- set detailed will automatically collect this roofline chart for you. It does require more work. So we'll now have to do a few more passes of this kernel, but then we'll at least get that roofline chart and it will tell us what the arithmetic intensity was. So I'll let that run. And then while I'm letting that run, let me just explain what the exercise is here. So we have a few kind of pre-written exercises that go through optimizing this kernel. And so we've learned so far that this kernel is compute bound, and we want to understand how can we optimize this. Well, and the steps like that I'm about to introduce are all shown to you in the top level README of the repository. So if you look at the README, it tells you how to walk through this GPP exercise, and then it basically describes what is going on in this kernel. Now, let's, is this done yet? Not quite. And so I want, like, our recommendation is that you actually do the work yourself and try to rewrite the code. But if you don't want to and you just want to like see the different profiles, what we've done is we prepared kind of like solutions for you. And so in this directory, example code GBP, we have patch files. And the patch file describes like what we recommend is a possible transformation of this code to optimize it. And there are a series of 4 cumulative patches that perform 4 steps of optimization on this kernel. And you can walk through them step by step. The README goes through the logistics of how to apply them, and then perform a series of successive optimizations. Now, the first thing that we want to look at is to understand a little bit about this kernel. So sorry, I just noticed a bit in chat. So let me go ahead and copy the thing that I was saying before. So if you're on Data GPU, make sure you do those 2 statements, and that will get the NVCC and NV4 training path. Okay, so what I was saying is that this kernel is compute bound, but we, typically what we want to do is we want to understand, are we at the limit? And the answer we can tell is no, we're not at the limit, right? We're getting 74% of peak throughput, but we are not getting 100%. And then typically what we want to do is look at this from a roofline chart perspective, or at least that's one thing we could do. So I'm going to go ahead and copy this updated report file down. Okay, so now we have a roofline chart because we did the -- set detail. You can see it took a lot longer to do, right? It took me nearly 3 minutes to click the profile, but so it can be painful for longer kernels, but we got it done. So what we see is the following. This is our point on the roofline chart. There's actually 2 points on this roofline chart. There's a single precision and double precision because, like, for whatever reason, the compiler generates a few single precision instructions for this kernel. This is such a tiny like performance number, and there are so few instructions that we can just ignore it. We know this kernel is double precision math, so let's just look at the double precision number. So this tells us that we have an arithmetic intensity of 9.2 flops per byte. That puts us just over into the compute bound part of the curve. On A100, the compute bound, the point at which it turns over is about 5 flops per byte. On a V100, it's about 7.5 flops per byte. So we're compute bound, not like overwhelmingly so, but we're doing enough flops per byte to be solidly in the compute bound part of this curve. Because we are compute bound, this gives us, my general thought process when we're in a scenario like this is, if we are compute bound, and the goal is to get from here up to here, right? The goal is to go from 3.2 teraflops to 7.6 or whatever. In this case, we have some freedom then to reconfigure our work to move up, right? We want to stay compute bound or roughly compute bound, but we can then think about re-optimizing our calculations to be more efficient. If we look at the scheduler statistics for this kernel, and if we look at, the launch statistics, we see that we are launching 65,000 blocks. And so the number of SMs on a GPU is like of order 100. And so then that means that I have plenty of blocks to fill the GPU. That's not in question. I'm launching enough work to fill the GPU. If I'm already launching enough work to fill the GPU, one can ask the question, is there anything that I might do in this kernel to increase the computational intensity of this kernel to give me a better chance of hitting the peak throughput of the GPU? So in that case, you can look at the loop pattern here. We have 3 nested loops. And each one of them, I have here in a comment, the trip count of each loop. And the trip count of each loop is of order 1,000 for the first two and 10,000 for the third one. Now, if you multiply any two of these numbers together, you get like a number that's like of order 1,000,000 or larger. And so as a result, we are already launching enough work for any pair of these two nested loops to fill the GPU. And so what we could try is to intentionally do one of these three loops sequentially per thread and have the other two be parallelized across threads with the hope that that will give us more compute work to do, right? Because any two of these loops collapsed together will give us enough parallelism to fill the GPU, because we only need like 100,000 or so threads to fill the GPU. And so we can take one of these three and do it sequentially, and then see if that gives us additional compute work to help get us closer to that peak. So that's what steps one of this exercise will be. You have to think carefully based on this kernel about which one of these three that you're going to do sequentially, and then which two of loops you will parallelize over. So that will require some thinking about the way this kernel works and what you know about memory access patterns on a GPU. And then there are further optimization steps as well that you can try if you want to go ahead and dig even deeper into this kernel. So that's the kind of layout of this exercise. The goal is to make it faster, but also as you go through each step of making it faster, then stopping and pausing to see what's going on with the profiler, and then seeing if the change in the roofline chart is consistent with what you expected to happen in that kernel. Okay, I think that I will stop there.